Hello everyone, I'm Liu Yang from DP1. In today's computer lab, we're going to have a taste in machine learning. To begin with, what exactly is machine learning? In essence, machine learning is a branch of artificial intelligence that allows computers to learn from and make predictions based on data. Unlike traditional programming where rules are explicitly coded, machine learning systems identify patterns within data and use these patterns to solve problems. There are two broad categories in machine learning. On one side, we have supervised machine learning, where the algorithm is trained on a labeled dataset, which means that each input is paired with an output, and the model learns to predict the output from the input. On the other side, there's unsupervised machine learning, where the algorithm explores the input data without pre-assigned labels to uncover hidden patterns. In supervised machine learning, a key distinction is between classification and regression. In classification, the goal is to predict a discrete label, for example, categorizing whether an iris flower belongs to a specific species. In regression, we aim to predict a continuous value, such as forecasting the exact value of the length of a flower's petal. On the other hand, in unsupervised learning, one common task is clustering, which involves grouping similar data points together. And it differs from classification because there are no predefined labels. In today's computer lab, we are using the famous iris flower dataset, which was originally introduced by the British statistician and biologist Ronald Fisher. The dataset contains measurements of iris flowers collected from 3 different species: Iris setosa, Iris versicolor, and Iris virginica. Each flower is categorized by numerical features such as the sepal length, sepal width, petal length, and petal width. In addition to these numerical features, there's also categorical data, namely the species itself. Next, I'll explain the k-nearest neighbors algorithm, or KNN for short. The KNN algorithm is especially useful for both classification and regression tasks. When applied to classification, it works by finding the k closest data points, which are the neighbors, in the training set based on a defined distance metric, typically the Euclidean distance. The algorithm then assigns the most common class among these neighbors as the predicted class for the new data point. Similarly, in the context of regression, KNN predicts a continuous value by averaging the outcomes of the nearest neighbors. In both cases, the performance of KNN strongly depends on the choice of k. If k is too small, the model might be very sensitive to noise, resulting in overfitting. Or if k is too large, the model might smooth out important distinctions, leading to underfitting. One effective method to choose the right value of k is cross-validation. Specifically, we're going to use leave one out cross-validation. The purpose of cross-validation is to check how well our model generalizes to unseen data. In leave one out cross-validation, we repeatedly take one data point out from the dataset, train the model on the remaining data, and test the model on that single point. This process is repeated so that every data point serves as a test case exactly once, and then the overall error is then calculated as the average error over all these runs. Now let's talk about the other category of machine learning, unsupervised machine learning. Here we are going to look at the k-means clustering algorithm. Unlike KNN, k-means is used when we don't have labeled output data. The goal is to group similar data points together based on their features. The algorithm begins by randomly initializing a set number of clustered centers, known as k-clusters. It then assigns each data point to the cluster whose center is nearest, using a distance metric such as Euclidean distance. After the assignment, each cluster center is recalculated as the mean of its assigned points, and these steps are repeated until the cluster centers become stable. When we talk about classification with KNN, The idea is to predict the species of an iris flower by looking at similar past examples. In my implementation, I first load my iris data and then sort the data based on how close each flower is to the new one that I want to classify. The distance between the flowers is calculated using a distance function implemented in the class iris that considers the sepal and petal measurements. Once the data is sorted, we take the first k flowers that are nearest. For these k nearest neighbors, we count how many times each species appeared and then convert these counts into proportions. Finally, the species with the highest proportion is chosen as the predicted species. As an example, when given the data of the first iris in the database, the algorithm predicts its species to be Setosa, which is correct. In the case of regression, our goal is not to decide a category but to predict a continuous value, which in this case is the petal length of a flower. The regression version works in a similar way. I started by sorting the iris data based on a distance function that is designed for regression, and this function focuses on features such as sepal measurements and petal width, leaving out the petal length, which we are trying to predict. After sorting, we pick the first k nearest neighbors and then average their petal lengths to obtain our prediction for the new flower. Instead of counting rows, here we combine the information by taking an average, which gives us an estimated value for petal length. When given the data of the first iris in the database, the algorithm predicts its petal length to be 1.46, which is close to the actual petal length of 1.4. A critical part of both of these approaches is evaluating how well our prediction works, and also choose the best value of k. And we do this by using a method called leave one out cross-validation. The idea is simple. Each flower in our data gets a turn to be the test case, in which one flower is removed at a time and the rest of the data is used to predict its species for classification or petal length for regression. By repeating this process for every flower, we can calculate an overall error rate for classification or the average error measured by RMSE for regression. This method helps ensure that our model performs well not just on the training data, but also on some new and unseen data. From the error rate plot plotted with k in the range of 50 from the training set, we can see that the error rate is at the lowest when k equals to 3. By comparing these two implementations, we see that both use a similar strategy of sorting the data to find the nearest neighbors. However, for classification, we base our prediction on the majority of occurrences among neighboring species, while for regression, we rely on the average of the neighbors' target values. Here is my Python implementation for k-means clustering. First, two small functions are designed to help with calculations, including distance that measures how far apart 2 points are on a graph, and mean point, which finds the center, which is the average position of a group of points, used to update the cluster centers. The plot clusters function draws a scatter plot to visualize the current clusters. It gives different color to each group and different markers based on flower species. It also shows where the cluster centers are by drawing large X marks. The plots are saved as image files showing how the clusters change over time. The KMC function runs the k-means clustering algorithm. First, it randomly picks k starting points as centers for the clusters. Then it goes through many steps where it groups each flower into the nearest center based on distance and draws a plot of the current clusters, and finally updates each center by calculating the mean position of its group. If the centers stop changing, the loop ends, meaning the clusters are stable. When three clusters are plotted, each cluster mainly contains one specific species. However, there are some outliers from each species. Setting cluster positions randomly in space can cause a few important issues in the k-means algorithm. First, if the random starting points are chosen poorly, for example, if they are all close together or far from the actual data, the algorithm might take longer to find the correct clusters. And also, since the starting positions are random, running the algorithm multiple times can give different results, which makes the outcome unstable and harder to trust. More, sometimes a randomly placed center might end up far from any data point, and in that case, no points get assigned to it, resulting in an empty cluster, which can end up in wrong results as it breaks the logic of the algorithm.